Okay, thanks, Peter, for the introduction, and thanks for to the organizers also for inviting us here to share with you our thoughts about membrane protein crystallization. This presentation has been put together by Jan Kubicek, who is also here in the audience, and myself. And Jan is also one of the co-inventors of the technology that's going to be the center of this presentation. So this is a workflow of a protein project. Obviously, we are here as it's about the crystallization of a protein, and in this case, membrane proteins. But I would like to say that also many of the upstream parts of this workflow are significantly important and can have a big impact on the final success. And as Peter has already said, the construct design is of high importance because it determines how much protein you actually get, and that means how much experiments you can do, and that finally influences the success rate. And I would like to make one point. We are consequently today using optimized constructs, optimized with respect to codon secondary structure avoidance and things like that today. And that seems to work quite well. And I will come to that later as well. So membrane protein crystallization is the topic. I probably don't have to say too much about the importance of membrane proteins. Not only that they make up approximately a third of the human proteome, which already makes clear that these proteins are important. It's also that 70 to 80% of all the drugs are actually working on membrane proteins or interacting with membrane proteins. So this number again says we have to work a little bit more on proteins. And these numbers here have been mentioned by Peter as well. So they're a little bit older, I think. There are 250 unique membrane protein structures compared to 70,000 or so soluble proteins. So obviously the traditional methods like classical vapor diffusion with or without detergents, as they have been developed for soluble proteins, they are probably not good enough. So there is obviously a need for an improved method. And what I hear today is that in the scientific community, the technology that is most seriously discussed to have the potential to overcome this lack in membrane proteins is the lipidic cubic phase. And this cartoon here, which is from Martin Caffrey, shall show how it is believed that the cubic phase actually looks like and works. So a cubic phase is made of a lipid, like for example monooleinine, that is capable of generating a bicontinuous three-dimensional structure of a bilayer system surrounded and surrounding water or buffer. And this bilayer system is shown here. So the monooleinine or other lipids make up such a bilayer. They are surrounding a water channel or a buffer channel, whatever your crystallization solution is, and they are surrounded by water. So that means N and C terminal domains of a protein can accommodate to the surrounding, and this system closely resembles the situation in vivo where of a cellular membrane. Now the membrane protein, as is shown here, can accommodate, can insert into this bilayer, and occasionally some of these proteins, that's the idea, can get into contact and finally form a kind of a lattice that can then ultimately lead to the formation of a protein crystal. So that's the idea how it could look like. I think it's not yet totally clear.